jump into the genetic playground. Remember that a single gene can have multiple flavors called alleles? In humans, the ABO blood type system is a classic example. There are three possible alleles, A, B, and O, but each diploid individual only carries two of them. When biologists started wondering what happens with all these alleles in an entire population, population genetics was born. Defining evolution in population genetic terms boils down to tracking shifts in how common an allele is. Let's say out of every 100 ABO alleles in a population, 26 are A, 13 B, and 61 are O. If the next generation's tally shifts to 30A, 15B, and 55O, we've witnessed an evolutionary change. Basically, any tweak in an allele frequency is a microevolution in action. Let's jump into the genetics playground. Remember that a single gene can have multiple flavors called alleles? In humans, the ABO blood type system is a classic example. There are three possible alleles, A, B, and O, but each diploid individual only carries two of them. When biologists started wondering what happens with all these alleles in an entire population, population genetics was born. Defining evolution in population genetic terms boils down to tracking shifts in how common a given allele is. Let's say out of every 100 ABO alleles in a population, 26 are A, 13 B, and 61 are O. If the next generation's tally shifts to 30A, 15B, and 55O, we've witnessed an evolutionary change. Basically, any tweak in allele frequency is a microevolution in action. Population genetics describes how common a given allele is in a population. Natural selection is one powerhouse way alleles can fluctuate. An allele that confers a survival or reproductive edge will get passed along more often. But since total allele frequency always sums to up to 100%, if one allele rises, at least another one must fall. If a super helpful allele emerges, it can become fixed, which means everyone in the population will end up with it. Likewise, a harmful allele might vanish quickly. And yes, we can actually watch this happen, like the famous peppered moth study, for example. When the tree trunks got more sun, got darker, dark-winged moths thrived. But when population dropped and the tree trunks got lighter again, lighter moths came back strong. Highly beneficial alleles may become fixed over a few generations, and every member in the population will carry it. More detrimental ones may be eliminated from the gene pool. British mathematician Godfrey Hardy and German physician Wilhelm Weinberg came up with an equilibrium, and it basically says that if no evolutionary forces act on a population, allele frequencies will stay the same generation after generation. Both Hardy and Weinberg each explained that dominant doesn't always mean taking over completely. Unless something like natural selection, mutation, genetic drift, or migration steers the pot, the gene pool will remain unchanged. In reality, though, every real-world population is getting nudged by one or more of these forces. So you'll never find a true Hardy-Weinberg scenario in nature. But it's an awesome baseline model to figure out who or what is rocking the gene frequency boat. The Hardy-Weinberg equilibrium states that allele frequency will remain constant if there are no evolutionary forces that act on a population. Now, let's talk about sexual selection, Darwin's special twist on natural selection. It's all about who gets to pass on their genes, typically leading to some flashy or competitive traits. See, during sexual selection, when a mate is chosen, that can either happen that two individuals compete for a mate. So we see those, for example, when two rams are butting heads, Or we can also have one individual choosing another mate. And of course, then that mate wants to be flashy and look good, like a peacock's feather, for example. So we have with intrasexual selection, which is when we have the competition, and we have of intersexual selection, when we're gonna have us one mate choose another one. So in intrasexual selection, we have us two individuals competing for one mate, often with a showdown, such as in two rams butting heads. In intersexual selection, one individual chooses a mate based on certain traits, such as a peacock's feather, something flashy. The problem is that these beautiful traits, such as the peacock's tail, can also attract predators. So nature balances, oh, you're so beautiful, with, oops, that hawk just spotted you. Population genetics shows us evolution is always happening. No population stands still. Sorry, Hardy Weinberg. And that's precisely what makes that natural world so exciting. There is constant change. Everything and all of that is wrapped up in some seriously cool genetic mechanics. All right. Remember natural selection? How certain traits give an individual an edge in its environment? That organism then is more likely to thrive and have babies, passing that helpful gene along. Over time, that allele, that gene becomes more common, and voila, evolution in action. So, anytime you see populations with certain traits becoming more prevalent, you can guess natural selection's at play. Some things are always favoring one phenotype and its corresponding allele, of course, over another. And that's a trait. Nature loves to remix, and stagnation is really not its style. So, in natural selection, organisms with traits better suited to their environment are more likely to survive and reproduce, passing on those advantageous traits to future generations, leading to the gradual adaptation of populations over time. And now, imagine your DNA as a blueprint for a house. Mutations are like small little changes and edits in that blueprint. It might be a moving of a door, adding a window, or do something that's not even noticeable at first glance. On a genetic level, that means mutations can swap an allele, a trait, for a different one, generating a new version of a gene. In the big picture, mutations are how brand new alleles appear in a population, providing raw material for evolution. By themselves, though, their effects tend to be subtle, like a single grain of sand on a beach. But combine them, these tiny little changes, with something like natural selection, and suddenly, if a mutation happens to be beneficial, it spreads over time. A harmful mutation is basically tossed out by natural selection. Critters with that mutation aren't likely to survive and reproduce. As a result, those bad alleles traits stick around only at low levels. A beneficial mutation, on the other hand, will slowly gain traction, generation after generation, as creatures with that allele and trait thrive more and more. Mutation is ultimately the source of genetic variation in every population on Earth. Without it, we'd have no new alleles to fuel all the crazy adaptations we see, like the finches at the Galapagos Islands, or even the differences among siblings. So, even though a single mutation is seen as a small, little change, it's like planting a seed that can, under the right conditions, grow into a whole new branch of the evolutionary tree. So a mutation is a random permanent change in an organism's DNA sequence which can be passed on to offsprings and in its future, and it is the ultimate source of genetic variation. Great, and then let's talk about genetic drift next.